Hey everyone, Mr. Newman here, and today we're going to talk about functions. First of all, a function is simply a relationship between variables. All right, that's it. There's some details about that relationship that we need to talk about, and we'll get into, but first let me show you some function notation. We've worked with lines, so y equals 3x plus 2 is nothing new, but another way to write that is f of x equals 3x plus 2. That means the same thing. So y or f of x. In this course, we'll often be using f of x a lot more. They're basically the same thing, y and f of x, but because both of them, as long as they indicate the output, and they will for the functions we'll be working with, then that's just fine. One nice thing about f of x is it shows you the input right there. So x is the input, and the output is the whole expression, f of x. Notice this parentheses, this does not mean f times x. That's a mistake a lot of students make. It's a different mathematical operation, and I kind of hate that how it's written. I wish there was another way to write it, but there's just that's the way mathematicians have been doing it, and so we just have to wrap our mind around that's not multiplication, that's function notation. So talking about input and output, so instead of y as an output, we could write f of x as the output, but a function always has an input and output. When I have a table like this, I can have inputs like 1, 2, 5, -2, and outputs that are associated with each of the inputs. So for an input of 1, there's an output of 3. Input of 2, there's an output of 6. And this table is one way to represent a function, just like up above, the equation is not related to the table, but that's a different way. An equation is a different way to show a mathematical function. And a graph is a third way to show a mathematical function. On a graph, the x-axis, horizontal line, represents all the inputs, and the y-axis represents all the outputs. So if I was graphing the table from right above, I would put 1 with an input of 1 and output of 3 would give me the point 1, 3 right there. Input of 2, output of 6 would give me the point 2, 6, and so on and so forth. Now, one thing that a lot of students mistake here is they think that a function has to be a pattern. There doesn't have to be a pattern for a function, just a relationship. So this function, even though it doesn't make any sense, I totally made it up, it represents a relationship. And if I tell you 2 is the input, then 6 is always the output here. So therefore, this is a function. Let's come back over here and let's talk about how we use function notation to evaluate functions. F of 2 just means put a 2 in for the input everywhere you see an x. So I'm going to rewrite my function f of x up there, but instead of x, I'm going to put parentheses so that I'm ready to input the 2. So when I plug in the 2, you notice I get 2 squared plus 3 times 2 plus 5. I have to put the 2 everywhere I see the x. And when you evaluate that, 2 squared is 4, 3 times 2 is 6, so you get 4 plus 6 plus 5 or 15. The next one's a little trickier because we have more than just a single constant that we're plugging in. Instead, I'm plugging in an expression, x plus 3. Again, I'm going to write my function and leave blanks where all the x's are, so I'm going to put x plus 3 right there where the function, right there where x was. Notice here, x is no longer the input, x plus 3 is the input, and I have to do that, I have to put that in everywhere there was an x before. So when you square that first one, you might FOIL. I don't use FOIL, I use the Punnett square, but you get x squared plus 6x plus 9, and then when you distribute the 3, you get 3x plus 9, and when you add all that together, you get x squared plus 9x plus 23. Again, I think we'll be practicing polynomial multiplication later, so if you're not sure how I got all those parts, we can talk about that in class. This last one, that's the answer. This last one, I'm going to start off with the same thing, but instead of plugging in x, I'm going to plug in negative x, and I get negative x squared plus 3 times negative x plus 5, and you get out a slightly different function than the original function once you simplify it. All right, let me show you how to graph these functions. If I have the function g of x equals x squared, I'm going to make a list of possible inputs. -1, 0, and 1 are often good ones to start with, and we can just see if they're on the graph. I'm going to plug each of these into the function. So I'm going to plug in -1. When you square -1, you get +1, so the point is going to be -1, 1. I'm going to do that with each of my inputs. And you notice I get a little, there is a pattern to this, but I'm going to plot those 4 points. So -1, 1, 0, 0, 1, 1, and 2, 4. And I need to connect these dots because this is a function. And I'll show you the reason I'm connecting these dots is because I could plug in decimals. For example, 0.5, when you plug it in, you get 0.25. And if I plug that into x squared, if I plug in 0.5, I get 0.25. That gives me a point, 0.5, 0.25. Well, I need to plot that point as well. So when I draw the curve that connects all those points, I'm plotting every single point on the function between each of the points I've plotted, and that covers all my bases. So when I have an equation, if you know what the shape of the graph should look like, we need to connect the dots. Let me do the same thing for the next one. -1, 0, 1, and 2 are good numbers to use. And I plug this in here. Here, 3 times -1 minus 2 is -5. So I get the points -1, -5, 0, -2, 1, 1, and 2, 4. Now, we just practiced graphing lines. This is a slightly different approach, just using inputs and outputs to generate points and then connecting those. But you'll get the same result as if you plot the y-intercept and then use the slope. In fact, you notice the y-intercept is just when the input x is 0. All right, so we got that graphed. Great. Let's talk about whether something is a function or not. We'll talk more about why this is, but something is a function if every input something is not a function if one input has 2 different outputs. If even one of them has 2 different outputs, is not a function. Like I said, we'll talk about why later, but let me show you this. First of all, I've got an input of 1, output of 2, input of 2, output of 4, input of 3, and output of 4, and every input has a different, every one input has a different output, so this is not true at all. One input has 2 different outputs because all the inputs are different. We're just fine here. So you notice this actually is a function. I want to draw this first because this often trips people up. Having multiple of the same outputs is not a problem. It's when you have multiple of the same inputs that there could be a problem. All right, let's try this one. Does one input have 2 different outputs? If you look right here, this is not a function because the input of 1 happens twice and it has 2 different outputs. The input of 1 has the output of 2 and the input of 1 has the output of 4. So this is not a function. All right, I'm going to put this last one up here and let you think about it and decide based on the definition, is this a function or not, and why? All right, we're moving on from this. Let's talk about the vertical line test. This is a quick way to see if a graph is a function or not. It is not a function if any vertical line hits more than 1 point. And we can talk about why this is. Let's draw a graph first. Here's just a graph of a curve. I'm going to draw a vertical line. And you notice my vertical line hit 2 points on the function. This means it does not pass the vertical line test and it's not a function. Why is it not a function? Well, let's look at those points. If I plot those 2 points or highlight those 2 points, they have the same input. In this case, the input is 2 for both points, but they have different outputs. And like we said, if there's one input that has 2 different outputs, like this, then it's not a function. So any graph, when you draw a vertical line and it hits more than 1 point, or it intersects more than 1 point, that is not a function. So this first one, not a function. Let's try this next one. Well, you can't just draw one vertical line, you have to try several vertical lines. In fact, ideally you try every possible vertical line. I'm just going to draw a handful. One good fast way to do this is if you have a pencil or a pen in your hand, and if you just hold the pencil or pen vertically and move it back and forth, you can see if your pencil or pen would intersect more than 1 point on the line. In this case, every single one of those vertical lines only intersects at most 1 point, so this is a function. It passes the vertical line test. All right, circles. We try one over here. It doesn't hit more than 1 point over there, but I need to try more. And sure enough, next one I try, the next vertical line I draw, hits 2 points. So this is not a function. It does not pass the vertical line test. All right, I'm going to leave you with a little bit of a tricky one. It is itself a vertical line. I want you to answer whether or not that is a function or not. All right, so some real world examples of non-functions. One example is a slot machine, because I've never been to a casino, but apparently when you put in money and you pull the lever, it gives you a different set of numbers. Sometimes people win lots of money, sometimes people win no money. So even though your input is the same every time, the amount of money you put in is the same, the output, the amount of money you win or you get out of the machine, is different. So that slot machines are not functions. Rolling dice is also an example of not a function. If you could roll 3 dice together, then you might get a different output every time you roll it. So that's not a function. Another example would be a game of Battleship. If you play several games, I might play a game with my brother and say B5, and it hits. In the next game, if I say B5, it's a miss. So that's an example of not a function. Domain and range is the last thing we got to talk about with functions. A domain are all the possible inputs, while range is all the possible outputs of a function. So when we're talking about domain and equations, there are 2 specific situations that are issues. If you have a 0 in the denominator, that is not possible. That does not exist. So any number that puts a 0 in the denominator must be outside the domain. You can't plug in a 0, or you can't plug in a number that gets a 0 in the denominator. Likewise, the square root of a negative number, that gives you a non-real answer, so we're only working with real answers when we're graphing right now. So if you have square root of any negative number, it could be -1, -2, -5, any number that gives you that will be outside the domain of the function. Let's look at a specific example. Right here, we say for the domain, x is in the set of all reals. That's how you write it. In other words, x can be anything. We can plug in any number into f of x here, and it'll be just fine, except for one number. The one number that would give us a problem is if we try to plug in -2. Let's look at what happens if we try to plug in -2. Do you all see the denominator right there? That, -2 plus 2 would be 0, and that would be a problem because that would give us 0 in the denominator. So that's why x can be anything except for -2. And this right here is how we write that. X is in the set of all reals, except, comma, x cannot be -2. For range, I'm going to do something similar. You can actually get any number out of this, and you can figure that out by plugging in or trying to substitute that number for f of x. Except for there's one number you can't get, and we're going to talk about later in the semester why this number in particular is a problem. But you can't get the number 3 out of this. If you want to know right now why, just a quick thing, you could try to solve 3 equals 3x over x plus 2, and you'll see what happens when you do this. Solve any other number, you can find out what x is. When you try to solve this, something funny happens. All right. For domain and range on a graph, the domain is how far the graph goes left and right. This is a little bit misleading here because this graph looks like it stops at the top up there, but as you guys know, when you graph, for example, this is a parabola, x squared, when you graph parabolas, they keep going up and to the left and up and to the right forever. That means x is in the set of all reals. In other words, x can be anything. You can plug in anything. You can have any input into this function, and you'll get out an output. Range is vertically how far up and down the graph goes, and here you can't get out anything. You can't get any output because this graph stops right there. It turns around right at y equals 1. So the way we write that is we say the range is y must be greater than or equal to 1. The reason it's or equal to is because it does include the point 2, 1. That point is on the function. So the domain gets all the way down to 1, so we have to say y is greater than or equal to 1. All right, for this last example, this is an example of a discrete function. In other words, there are just specific points in the function. We don't have any other information, no graph, no equation. So the domain is only what we see there in the x column. The domain is 1, 2, or 3. Or sorry, and 3. The range is just what we see there. So the range is 8 and 5, and I put curly brackets around that. All right, thanks for watching.